Okay, so this video is going to talk about moments of forces. This particular video is just going to talk about what a moment of a force is, what it actually means, and then go through a really simple example. There's a very strong chance that my cat is just going to walk in front of the camera in a minute. Sorry. This is Palace, everyone. Hello. A moment of a force is the turning force, like the turning effect of a force. So if we think about a real life example, so if you think about one of those fire escape doors, to excuse my terrible drawing, there's some hinges, and then if the door was being held open, so it's got one of those things on it that automatically shuts a fire escape door. Okay, so trying to pull it shut that way. Now, if I asked you to go and hold a door open, it would be most sensible, and I think most of you would put your hand here. So you would hold the edge of the door. If I then asked you to put your hand near the hinges but use the same amount of force, you'd find it much trickier to hold the door open. So that's because if you apply a force near to a pivot point, so the distance away from the pivot point is quite small, it has much less of an effect, it's much harder work than if you put the same force, you apply the same force further away from the pivot point. So that's all taking moments into account, really. So to calculate a moment, the moment of a force is the force multiplied by the perpendicular distance away from the pivot point. And the units that we'd use for it, so distance is going to be measured in meters always. Our forces are going to be in newtons. So the unit of a moment is Newton meters. Okay. So let's think about a simple example using this. So we're going to think about a uniform plank. So most of the work that you've done in mechanics so far is just modelling things as particles. This time we're going to think about uniform rigid bodies like this plank. So uniform means that its weight is evenly distributed throughout its length, and it being rigid just means it doesn't bend. So this uniform plank is going to weigh 30 kilograms. So because it's uniform, that means that in the middle there's 30G acting downwards. I'm going to say that the plank is 5 meters long in total, and that it's resting on 2 supports, so one there and one there. Okay. Let's call that point A, that point B, that point C, and that point D, just so we can refer to them later. This distance here, I'll tell you that is 1 meter. This distance here is 1.5 meters. This one's 1 meter, and this one's 1.5 meters. So we've got our 30G acting downwards there, and the only other forces that are acting on this plank are these 2 supports are providing a reaction force. So I'm going to call that one RB, and I'm going to call that one RC. Okay. And in this question, I'd like us to find RB and RC to find the magnitude of RB and RC. So I'll tell you that the plank is resting in equilibrium. So that means that all the forces are balanced. So this force and this force must be equal to this force, because if it's in equilibrium, all of the forces acting upwards must be equal to all the forces acting downwards. So we could start by writing that. So up equals down. So RB plus RC equals 30G. So we've still got two unknowns there, but that's okay. We can come back and we can use this later. The next thing that we're going to do is we're going to think about taking moments about a point. Now, it's sensible to take moments about one of the pivot points. Okay, and that's because as we calculate a moment, we will look at the clockwise forces. So this 30G, if I was to take moments about B, this 30G would be acting clockwise. So it would be dragging, if I put my pivot there and fold this, it would be taking it round in a clockwise direction. And again, if I put my pivot there on B, this RC would be acting in an anti-clockwise direction, so moving it that way. And because we use the calculation of force times distance, 30G times 1.5 and RC times 2.5, it will completely eliminate RB from my calculation because the distance of RB from B is 0. So it's just going to allow us to work out RC. So let's start by taking moments about B. So because it's an equilibrium, we know that clockwise equals anti-clockwise. Okay. So the clockwise ones, this one here, the force is 30G and the distance is 1.5. That's the only clockwise force there on this plank. And then the anti-clockwise, the only anti-clockwise force is this RC. So it's equal to RC times the distance, which is 2.5 meters away from B. So if I rearrange that and put it in my calculator, RC is equal to 30G times 1.5 divided by 2.5. So it comes out of being 176.4 newtons. Now we've got two options of how we find RB. So we've got RC. I'll write that up on my diagram so that I remember that I found it. We've got two different ways that we could find RB. The easiest way is probably to use this thing that we've already written down. So if we go back to that, RB plus RC, which is 176.4, is equal to 30G. So if I rearrange that, RB is equal to 117.6 newtons. So that's probably the easiest way. But if you wanted to practice taking moments, we could also find RB by taking moments about RC. So let's just do that just to check we get the same answer. So let's take moments about C. So because it's an equilibrium, I know that clockwise equals anti-clockwise. So this time, this is my pivot point here. So a clockwise force is this RB. So if I put my finger on the pivot point and then follow this round, that one's going in a clockwise direction. So RB is going in a clockwise direction. and RB is 2.5 metres away from C. So RB times 2.5. And then the anti-clockwise force. So again, if I put my finger on the pivot point, 30G is the anti-clockwise one. So if I was to follow it around there, it would move that anti-clockwise. So 30G, and it's 1 metre away from C. So 30G times 1. And if I rearrange that, RB is 30G times 1 divided by 2.5, which comes out as 117.6 newtons. So we get the same answer as we did there. So we know we've got it right. Okay, that's it for this one. The next video will be a couple of slightly more complicated examples.